All right, let us get started. I'm sure none of you would need my introduction of Professor Wen, but please give me 5 minutes to do my job because first of all, I'm given this task. And second, we also need to give some time for people to be slightly late and for them to settle in. So Professor Xiao-Gang Wen is a world-renowned theoretical condensed matter physicist and is currently the Cecil and Ida Green Professor of Physics at the Massachusetts Institute of Technology. He is widely regarded as a pioneer in the field of topological phases of matter, and is in fact credited with introducing the very notion and the basic definitions in this very important field. Despite being trained initially as a string theorist under Edward Wheaton, Professor Wen has made remarkable contributions to condensed matter physics throughout his illustrious career. His exceptional ability to identify defining features of physical phenomena and abstract suitable mathematical frameworks has led to significant advances in our understanding of physical systems, which range from high-TC superconductors like cuprates to fractional quantum Hall states and beyond. Professor Wen's work has had a profound impact on the field of condensed matter physics, and he is considered one of the foremost experts on the emergent phenomena in quantum materials. So the previous line was actually from ChatGPT, and I think that was a severe understatement. So the following line is from me. I dare say practically every condensed matter theorist trained in the past decade is a disciple of Professor Wen's in one form or another. As a deep thinker, Professor Wen has demonstrated repeatedly that great physical insights and clarity can arise from simply contemplating on the fundamental meanings of basic sounding terms, like what it means to say we have a phase of matter, or what it means to say we have an excitation in the system. My personal favorite along this line is his famous enigmatic but charming remark that a Fermi liquid is not a quantum liquid at all. I think maybe we should make it a compulsory question in all the qualifying exam for condensed matter theorists. So as a creative theorist, Professor Wen has surprised the condensed matter, high energy, and quantum information theory communities multiple times by showing how disparate physical phenomena and abstract mathematical ideas are in fact two sides of the same coin. As an avid educator, Professor Wen has successfully disseminated his wide-ranging ideas through his more than 400 published works and also 2 textbooks, one of which he co-authored with Professor Beijing in our department. As a diligent student, yes, I said student, Professor Wen is still craving for knowledge, and his energy for doing so seems to be boundless. In fact, he just told me yesterday that he wished he could be a student again and spend 1 year doing nothing but to learn about non-commutative quantum field theory. His passion for knowledge and learning is an inspiration to all of us who know him. But Professor Wen, we already have a very difficult time playing catch-up with you. So please, maybe you could relax a little and give us an easier life. Professor Wen's contribution to physics have, of course, been recognized with numerous awards and honors, including membership of the US National Academy of Sciences, the Oliver E. Buckley Prize, the Lars Onsager Prize, the Dirac Medal, to name but a few. It is a great honor to welcome Professor Wen as a speaker of the IAS Distinguished Lecture at HKUST today. He will be telling us about the origin of light and electron and new topological matter. Please join me in a warm welcome.
Yeah. Yeah, thank you, Adrian. Yeah, it's a really very warm remark. It's really a great pleasure for me to come to Hong Kong and to HKUST. And I remember my first time come to HKUST is just when this university just started. That there are only two grades of undergraduate, just a freshman and a sophomore. And so it's very early days. And I still remember the first impression when I come to the front. I see the building. This something coming from the future, the Star Trek, and so it's really amazing. HKUST kind of take off so quickly, and it's a really amazing story. And it's really great pleasure for me to come back, especially after the pandemic, and kind of start to reconnect after 4 years. Yeah. So today I'm going to talk about something about origin of light, and also this connection to some kind of topological matter in condensed matter physics. So we know that a science exploration usually starts with a question, and so the question we like to ask is what is a light? Then obviously you may say, oh, this is something from the sun. Okay, but that's not what really we ask. we really want to ask what is this thing, you know. And in the early days, there's two schools of thought. One thought is that the light is a ray of a particle. Another thought is light is a ray of a wave. So just like physics, you know, particle theory, wave theory, just two theories, you know. And so my son told me in their high school, the theory means something not true, you know. And so that's just theory, you know. Everything is just theory means something not true. Okay. So we need to let the experiment decide which theory is correct. And here, the experiment we can do is this diffraction, refraction, not refraction of lights. And so we can pass light in a piece of glass and to see how much they bend. You know, they can bend. And according to particle theory, that you may assume the surface of a glass have attractive force. So pull the light particle down into the glass, and then it's getting faster. Okay. But in the wave picture, you have this motion for this wave front. Then in order for wave to bend downwards, the wave front need to move slower in order for it to bend downwards. So actually, the particle theory and the wave theory have an opposite prediction in the glass, whether the one goes faster, another goes slower. And then we actually, using this measurement, we can actually do the measurement. The measurement is that actually the light in the glass is slower. So that means the wave theory wins. Yeah. So the light should be a wave. Okay. But this, using this wave theory, actually, we get a lot of insights about light, because wave have a character as a wavelength, also have a phenomenon of interference, you know. And if two waves line up with a peak to peak, valley to valley, this wave would add up, get stronger. If the wave line up, two waves line up with a peak to valley and valley to peak, then would cancel. Okay. So this is a new phenomenon from the wave theory. So therefore, the wave theory not only require the speed of light to be slower in the glass, also have new predictions. And then you should seek for this new prediction and to see whether wave theory really holds or not. So indeed, this new prediction from wave really holds, and we can observe the interference phenomenon of light. So it's just like a two pieces of glass, one piece is flat, another piece is curved. And then when the light going through this two surface, it can be reflected in two places. And so you can see the light goes through different paths, different lengths of paths. So depending on this length of path, sometimes they have a constructive interference, sometimes they have destructive interference. For example, in the middle of a glass, these two paths are about the same length, so they always have a constructive interference. So these two waves just add up. And but then away from the center, the two paths have if the two paths lengths have a separation about half a wavelength, then you have a destructive interference. You get black rings. So this is a prediction from the wave theory. So that's further confirmed that indeed the light is a wave. But also we learn more. This is a diffraction, this interference pattern from this just green light. You have a white light, then you'll see the color. Okay. If you look at it more carefully, you'll notice that the inner ring is kind of reddish, and that means this part is missing blue. At the inside this ring, so you're missing blue. That means the dark ring of blue is closer to the center than the dark ring of red. So in the middle, you're missing blue first, then you start to missing red. Okay. And that means that because blue is closer to the center, so the destructive interference happened earlier. So that means their wavelength is shorter. Okay. So just from this, we suddenly have another realization. The color is wavelength, and the blue means a shorter wavelength. show. That's an experimental fact. We can do using experiments to obtain this common knowledge now. So the blue is shorter wavelengths, red have a longer wavelength. However, this wave theory for light also provides a lot of challenge, because we usually think vacuum is empty. If vacuum is empty, then the light traveling in the vacuum, it's much easier to view them as a beam or particle. Something on the vacuum is moving around. Okay. However, it's much harder to thought light is a wave. If indeed the light is a wave, because that's an experimental fact, so we cannot dispute with that. So that almost means the vacuum actually is not empty. So the vacuum is something like some media. And so people strongly believe such a media is there, and even gave the name called ether. Okay. So in some sense, the light is vacuum is not empty, some dynamical medium like an ocean. Then the light is like a wave in the ocean. Maybe some other particle is like matter is like a bubble in the ocean. So this again, this is simple experimental fact that light is a wave. After human imagination led to vacuum is not empty, and some very deep foundational question. Okay, so if you really believe vacuum is not empty, it's a dynamical media, so there's an issue. What is this media looks like? And one simple example, simple assumption, we can assume this vacuum is a liquid of particles, a lot of particles moving around like a gas, some liquid. Okay, so we can see that my vacuum is a millet porridge. Okay, so this is a picture of a millet porridge. Okay, and then what is the wave in this millet porridge? It's a density wave. So somewhere the millet is more, otherwhere the millet is less. Then you have density wave, just like the animation here. That's the density wave. The density can propagate, and that's a light wave. So that's the picture. Okay. However, this picture, again, this is theory. This is millet porridge theory, okay? This theory have predictions. This density wave is a so-called longitudinal wave. In a sense, in order for the particle, in the direction, the propagation of the wave is in the horizontal direction, but the motion of a particle to generate this wave also kind of horizontal. So then that's causing a change of density. And so this, in physics, we call this a longitudinal wave. So the direction of propagation and the direction of particle motion is in the same direction. And that's causing the density modulation, and that's a longitudinal wave. Okay. And there's also transverse wave. That is the wave propagated horizontally, but the particle just vibrate vertically, kind of doing this shear deformation. But however, the millet porridge have a prediction. We don't have a transverse wave, because a shear deformation do not change density. So it's actually this simulation. Indeed, I do shear deformation. You can see from the edge. You can see we do shear deformation of particle, but shear deformation do not cause any change of density. You don't see anything. So shear deformation for the millet porridge is a do nothing deformation. They do not do anything. So there's no transverse wave. So therefore, this theory predict that. Again, this is theory. The theory predicts that there's only one mode, and this mode is a longitudinal. Then we can go back to the experiments, whether light wave in a vacuum indeed have only one mode, and is a longitudinal mode or not. So we can really check whether this millet porridge theory is correct or not. Then you find actually it's incorrect. So light actually is a pretty interesting story. So it's not that easy. We know it's incorrect because there's phenomenon of birefringence. There are certain crystals when light passes through that, the light beam can split into two. So that suggests that actually the light wave have two different modes. When they enter into crystal, they may bend differently. So therefore, this light wave actually have two modes, not just one mode. Okay, and these two modes actually both are transverse mode. There's no longitudinal mode. To see this, really, we have to play with the polarizers. Okay, so actually we can using one polarizer to polarize the lights, and using another polarizer to see whether this light can be blocked or unblocked. The reason we know both waves both modes are transverse because we can unblock light wave by rotating this polarizer, So if you have longitudinal mode, it just goes this way. It doesn't care whether you rotate the polarizer or not. So longitudinal mode cannot be blocked or unblocked by rotation polarizer. The fact that we can block or unblock them means both modes are transverse mode. Okay. So therefore, basically this really say that our Millet porridge theory is wrong. This will give rise one longitudinal mode, no transverse mode, but light is two transverse mode. Okay, so as a theorist, we can always think of another theory. Actually that's good. The theory is wrong. It's a good thing. That's we have a job to do. So we can invent another theory. If it's wrong, we can get another theory. Then we never lost a job. And so then another interesting, but to invent a theory is hard, How do you invent a theory? Well, just pick one, Don't even think, just pick whatever comes to your mind first. And then try to think whether your guess is right or wrong. If it's wrong, it's okay, then you just pick another one. Because once you're making those wrong guess, you start to have a sense where it's wrong. So when your next guess, you may improve it. And to think to have a right theory, right idea at the first time is almost impossible. So it's always you always have a wrong idea, wrong thing. But that's fine. The wrong thing is a good thing. But you should have something, and just think whatever thing. And so we just randomly pick another thing. So we can have this array of particle, just a particle form array. Or another, you can say that's like a ball spring model. There's a ball connected by spring. So this is another model for the vacuum. Then this ball can move around. They interact via these springs. They can move around. And then you get waves. Here, similarly, you have a density wave, just like this animation. But then for this ball string model, you also have a transverse mode. Because now the shear deformation is not a do-nothing deformation. It's you change the configuration, the cost energy, and so we have both. And actually, you have two transverse modes because for propagation in the horizontal direction, we can shear up and down or front and back. Have two directions. So therefore, we have a three mode, one longitudinal, two transverse. Okay. So now we know that although it's nice to have a different thing, but also not right. And these two examples also reflect something we call the principal emergence in condensed matter physics. That is a physical property for material depend on the ordering of this of a thing which forms the material. In the first Millet porridge, we have random distribution of particles, and that only gives us a longitudinal mode. And here we have regular distribution particle, which gave us three mode. So in a sense, the origin of a wave equation coming from the ordering of those particles. So that's order gave rise to property, gave rise to wave equation is really one way to say that's a principle of emergence. Okay, so we are stuck, actually. And, after Maxwell find his equation, and we just don't know what is waving. And actually, we try many things. Not only this Millet porridge and this ball spring array, we've tried many other things. We get all kind of wave equation, but none of them like a Maxwell equation. None of them give rise to two transverse mode only. Okay, so so that's what we do. So we say light is fundamental. Don't ask. That's one way out. Otherwise, as a teacher, we cannot answer everything. That's a way to hide. But however, as a physicist, we're really curious. So those questions kind of keep bugging us. We keep that in mind. So what is origin of light? Although officially we say it's a fundamental, don't ask, but we still asking ourselves privately, and hopefully maybe we have some idea some later days. And recently we do have a breakthrough actually, and so we should think about this liquid of strings. And so it's really the noodle soup. Okay, the vacuum is a noodle soup. Okay, and so why noodle soup works? Certainly, first this noodle soup the noodle is very long, have no end. It's a very long noodle which you have in your birthday. And so certainly in the noodle soup, the wave is also density of noodles. Somewhere have more noodle, otherwhere have less noodle. The density of noodles. And but however, for the noodle soup, there's a thing. The density of a noodle cannot change along the direction of a noodle. If noodle cannot end, then along the direction of noodle, the density cannot change. In order for density to change, noodle have to end. Okay. So therefore, density of a noodle can only change in the direction perpendicular to the noodle. Okay. So that is really this animation indicates. This animation. Well, my computer is very slow, but you can see it. And so then therefore this you can see the propagation of the wave and the orientation of a noodle happen to be perpendicular. So that gives rise to transverse mode. And propagating this way, noodle can orient aligned up and down or aligned back front. Okay. So that's it. And so the density wave of a noodle happen to have only two transverse mode and no longitudinal mode. That's just like a light. Okay. Okay, and so it's kind of embarrassing. The answer is so simple. We should have thought this 100 years ago. Why take us 100 years to think to go from particle to noodle? It's noodle. That's it. And so this really became an issue. Do you really believe this noodle soup theory of a vacuum? And so here I try to say that it's not just me saying that. Even some expert, actually it's 美食家, they have a book about the noodles, and they really say that a bowl of noodle is a universe. So that's really what I'm saying also. And so actually, like our story of light is a wave. When you say light is a wave, there's prediction. Actually, there's other predictions. So there's many predictions which all those predictions come together, which enforcing us to say, oh, light really is a wave. So here I just want to say that the wave have two transverse modes, just two evidence. Maybe light is a noodle wave. Maybe but this noodle soup theory may have even more predictions. If you see other predictions that may enforcing us, this theory maybe is really true. Okay. So this noodle soup theory not only explain the origin of light, it also explain the origin for electric charge. Okay. So let's see whether it's working or not. Okay. So this you can using the fur and some kind of plastic to make a electric charge, and you can see this rod electric charge can interact without contact. Yeah. So this is just say there's some electric charge. Basically, it generates electric force which can interact without contact. So this is another new phenomenon. So basically, what I try to say is that this noodle soup theory also explains this phenomena of this electric force and electric charge. Okay. So so how that works, and the first, as some kind of philosophical thinking, we don't believe non-contact force. Okay. In just in demonstration, looks like the ruler and the rod don't touch and then still interact. Okay. But as a physicist, maybe as some philosophical preference, we don't believe non-contact force. So we believe the following. There is so-called something called the electric field. Okay. And electric charge can generate electric field. And electric field, in turn, act on other charge. That's how the electric force was made. So first charge generates electric field, then electric field acts on the second charge, and that's how we explain the electric force. Okay. And so, yeah, I think if I have some balloon, I probably in the winter I can even do this demo. These two balloons, they charge, they repel like a non-contact force. But actually, but why do we want to introduce a field? In some sense, field is kind of abstract, but actually not that abstract. Like this, this angel would have a field around here, and this Jesus also have a field around her. So we do have that concept of field. So imagine the electric charge also have something like that. Okay, and so using this kind of picture, and then we can say that electric charge is something generate electric field. But then we realize that the end of string generate a string density. Just like the picture. So we have an end of string, then a lot of string coming from the end of string. So end of string is a source of a string density. It's just an electric charge is a source of electric field. So there's an analog. So therefore, we can really say that maybe the end of string is electric charge. So this is an outcome of this noodle soup theory. We can assume again another theory. The end of string is electric charge, which generates the string density, and the string density is an electric field. And the string density can interact with another end of string, and that's what we see as an electric force. So this is really the picture. And so once we have this picture, we have another prediction. That's kind of amazing for the theory. You have a lot of guess, a lot of theory, which is supposed not true, but the theory have a lot of prediction, and you can check the prediction, and then it turn out the theory actually is correct to some degree. So when the electric charge are moving, and oscillating, then this string density would also move around and propagate. Then you generate this string density wave. That is light, And so this wave generated by electric charge can be done. This experiment. So this is I think there's some kind of electric fly killer. If you break it up, you can generate a very high voltage, and so there's a neon bulb on the other side. Okay, and so these two long wires like antenna, and so that is the neon light bulb, and you just generate some electric pulse. I don't know. Yeah, you can see there's the other neon bulb have some reactions. So there's been something, the wave generated and then go to the other side. So there's some experiments to do that. Okay, and so So actually, this is the story of Maxwell, actually, what we're describing. You know, in around 1865, Maxwell write down his equation, which unified three very different phenomena. But actually, Maxwell's equation is supposed to unify two phenomena: is electricity and magnetism. You know, and then they find that this electricity and magnetism can have distortion, can be wave, can propagate. And then using the experimental measurement, they calculate this the wave of electromagnetic wave have very, very high velocity. It's amazingly high. And happen to be close to the velocity of light. And then Maxwell bravely conjectured that this kind of electromagnetic wave actually is a light. Because at that time, light wavelength is very short. It's very hard to view that as a wave. Okay. So therefore, it's a wonderful revolution in physics that the very distinct phenomena are unified under one theory. But certainly we have trouble because after Maxwell wrote down his equation, we don't know what is waving. You know, we know the light or electromagnetic wave is a wave, but we don't know what is waving. Actually, Maxwell, that's really the Maxwell's paper. You know, he draw this gear model. So have a gearbox theory. You know, those gear are turning around, and this small gear kind of running around, and that gives some kind of wave and the currents. You know, that is his. So it's not merely the porridge theory or not noodle soup theory, but they have a gearbox theory. Okay. But I don't understand why Maxwell draw this picture, because obviously hexagonal gear cannot turn, you know. It should not work. But I don't know, maybe as a theorist it's okay to draw a hexagonal gear, assume it can really turn. But now, you know, we don't have this gearbox theory. Actually, we have this noodle soup picture. So it's kind of different picture. But actually, for the people in quantum, actually, it turns out this gearbox theory and the noodle soup theory is not that different. It's really that there's a famous thing about the quantum mechanics. When the gearbox is turning, the turning gives you angular momentum. The angular momentum is quantized. Then the quantization of angular momentum tells you whether there is a string or no string. So angular momentum 0 means no string, and 1 means that there is a string passing that gear. So there's a duality picture. So actually, on the duality picture, the noodle soup theory and the gearbox theory actually is the same. They are dual to each other. But this is need more advanced quantum mechanics to understand that. So in some sense, we are going back to Maxwell. We just do quantum gearbox model, and that's gave rise to this noodle soup picture. So actually, so Maxwell's picture is not wrong. And so I just talked about this the light wave, and also understood as a charge, as an electric charge. So in some sense, this electron is like an electron. So you can view that the density wave string is a light wave, the end of string is an electron. So we have some kind of understanding or unification of electron and electric force and the light. But however, our nature is more complicated, actually. Our vacuum is more complicated. Because our vacuum not only have an electron, also have a quarks. Not only have electromagnetic wave, also have gluons, or maybe you can say Yang-Mills wave. It's another different kind of wave, satisfy Yang-Mills equation. So there's an issue whether this Yang-Mills equation or Yang-Mills wave are responsible for weak interaction and strong interaction. And then you may say that, yeah, if using this noodle soup picture, you can explain origin of electrical magnetic interaction. How do you explain origin of strong interaction and weak interaction? How to explain the Yang-Mills equation? How to explain the gluons? You know, and it turns out that it's not too bad actually. if you assume this our noodle have a different type, like a blue noodle, red noodle, and a green noodle, and then this noodle can join in under certain rules, under certain rules, and then you get this so-called stringlet liquid. So it's kind of more complicated version of noodle soup. Yeah. It would be nice if some restaurant provide a stringlet noodle soup. And then actually, when you have this kind of stringlet soup, then you can have this Guluang Yang-Mills equation. And for people who know a little mathematics, is that the Yang-Mills equation related to group. And so actually, the group have this representation, and there's each is different type of string, like a different representation. And the joining rule is that if all three representation can contain trivial, tensor product contain trivial representation, then they can join. So therefore, this group are hidden in the joining rule. So this Yang-Mills equation are really the hidden here. Okay. So at the end, what we find is that if you assume our vacuum is this stringlet liquid, so actually what we can have electron and a quark, which appear as the end of string. We can have electromagnetic wave and the Yang-Mills wave as a density of the stringlet wave. And so that's almost everything about the elementary particle. So almost all the elementary particle can originate in this way. So therefore, we call this a kind of a great unification. Because the grand unification is a unification which unify all the three interactions, but do not include the electron and quark. And this great unification is unify interaction and the electron and the quark all together. So therefore, it's possible to have this all the element particle and all the force coming from this stringlet liquid. I want to say that there's one thing we don't know is gravity. So gravity interaction is not in this picture. This is still open question. We don't know how to get the emergence of gravity. Yeah, so this is still open question. Okay, so here let me just go forward. Just spend a little more time about this unification of gauge interaction and the electron and quarks. So far what I'm talking about do not rely on quantum mechanics. So I hope you can understand that without knowing quantum mechanics. But this slide and next slide would require quantum mechanics. Okay. And so first thing within quantum mechanics, we have two kinds of particles, the boson and the fermions. The electron quark are very special. They are fermions. They have these fermion properties. Okay. And I don't know, people even don't ask where fermion come from. It's just that they're fundamental, they're given, just don't ask. Okay. But you can be brave, you ask where fermion come from. Okay. I think in undergraduate, when you learn quantum mechanics, you say fermion come from this anti-symmetric wave function. Okay. And when you go to a PhD program, a graduate student, learn quantum field theory, you say, okay, fermion from Grassmannian valued field. What is that? That is a fermion. So the point is that the fermion sounds like a very, very fundamental properties. It's just a given. We really cannot ask where it's coming from. But however, this string picture can really explain this origin of Fermi statistics. And because they all come from strings, so in some sense, the gauge interaction, so this electric interaction, the gauge interaction, and the Fermi statistics, actually is related. It's coming from same source. It's just two sides of the same coin. So we have this unification of gauge interaction and Fermi statistics. And so basically, the string density is the gauge interaction, and the string n is Fermi statistics. Okay. But to explain Fermi statistics is not so easy. So let's explain something simpler. Fractional angular momentum. we know that in the hydrogen atom, the orbital motion always gives you integer quantum angular momentum. So it's very mysterious. Electron have a half integer quantum angular momentum. You know, I remember when I learned this, I feel really mysterious because angular momentum means there's an electron have internal structure, and something moving give you angular momentum. But something moving always give you integer one, but how to get a fractional one? So that's another puzzle. Okay. So actually, we can understand the puzzle of a fractional angular momentum using the string picture. So so here I want to say that the string liquid, actually is a quantum liquid. So this is really the quantum thing. So which really means that we have a string ground state wave function, which is a superposition of all different string configurations. So this, when we say string quantum liquid, it means the wave function of a string is a superposition of all different string configurations. This is really a quantum concept, so I need to use this quantum concept to explain this. Okay, so in a sense, the coefficient of this superposition we call the wave function. This wave function always equal to 1. It means that for all the string configuration, the string wave function always equal to 1. And in particular, if a two string configuration differ by this string reconnection, the wave function will have same amplitude. So therefore, the string wave function have this property. When the string move around, they have same amplitude. When the string reconnect, they also have same amplitude. So the wave function have these topological invariance. Okay. So this is some preparation. So the end of a string will be so this end of string, the string may just go downwards. Okay. And then the string can fluctuate. It may go downwards and then go around, and may go downwards but go around in another direction. So all these string fluctuations are there. So end string is not just single string configuration. It's a superposition for many string configurations. Again, that's a quantum notion. Okay. So with this preparation, we can try to understand the angular momentum of a string end. To see angular momentum, we just rotate the string end. What we do is that we do this 360-degree rotation. Okay. Then we find that this straight end turn into the hooked end. You do 360 rotation. And then we know the string can fluctuate. But then we realize something interesting. The string can fluctuate, but no matter how string move around, it's still hooked. But the string can reconnect. But when string reconnect on this small neck, then the right hook became left hook. But still hooked. So never go to straight. So there's no way for string, no matter how they reconnect, how they deform, this right hook, left hook can never go to straight. Suddenly realize there are two sectors. One is the straight sector and the hooked sector. When you do 300-degree rotation, you go from straight sector to hooked sector. Then in quantum mechanics, we get this 2x2 matrix. So this 300-degree rotation acts on these two sectors using 2x2 matrix. And this 2x2 matrix have two eigenvalues, +1, -1. The -1 eigenvalue means that the wave function changes sign by doing 360-degree rotation. And that's half angular momentum. Yeah, because 300-degree rotation, 2-pi rotation, supposed to go back to the original wave function. You have minus sign means fractionalized angular momentum. So immediately we see that this kind of combination have a spin 1/2. Yeah. So therefore, this end of string naturally have a fractional angular momentum. So actually explain the origin of a fractional angular momentum. And also, fractional angular momentum also imply this Fermi statistics. Again, using this cartoon, we can explain that. So we have a two string end. They go both straight, let's assume. Then we try to exchange the two string end. It's very important that we should not rotate the string end. So when we exchange them, they still string still going downwards, leaving the end of string. So we don't rotate. Okay. And then we can do a reconnection. We can reconnect this neck, then became this one. We can reconnect another neck, then became that one. So after two reconnection move, then we find that exchanging two particles is like rotating one particle by 360 degrees. Okay. And so therefore, if a rotation by 360 degrees gave us a -1, that means exchanging two also gave us a -1. That is Fermi statistics. Okay. So again, this understring can explain this Fermi statistics just using this cartoon picture. So the bottom line is that what we think about something very fundamental like a gauge field, gauge interaction, electromagnetic interaction, Fermi statistics, the fractional ornamentum, something very fundamental. Actually, it's not that fundamental. They all come from a certain organization. And this organization is described by this string liquid. This string liquid organization actually naturally gave rise to this, which we originally thought to be a very fundamental property. But actually, they are just a derived property of very simple quantum string liquid. So that's basically the power of emergence. The emergence, some very fundamental property can be emergent. Okay. So then one may ask, where string come from? You say, oh, vacuum is string liquid, but where string come from? That's one question. Another question one may ask is can you realize a string liquid in condensed matter system in some material? And then we have this light wave in that material. Okay. So in some sense, we can say that actually the string can come from, here I want to say the string can come from the electron spins. So which can be, this string liquid can be realized in some material, in some magnetic material. In the magnetic material, the degree of freedom is just electron spin. Electron spin can be up and down. Okay. So we can imagine we have a material where this spin up is like a reference, like a vacuum, a nothing, like reference. And spin down means the presence of a string. Okay. Then therefore, this string down may line up to form a string. So you can imagine we can design some interaction between spins where the spin down want to line up to form a string. And the end string costs energy, so they do not want to form end string. But without end string, the string don't cost any energy. And also string want to move around, And then this is the situation, if a spin have such an interaction, then we can realize a string liquid in the magnetic material. Okay, so this is this string liquid will become some kind of ground state of this magnetic material. So in condensed matter, that will be a new state of matter, string liquid matter. Just like a superfluid is a particle liquid matter. When particle liquid at a very low temperature and still have a liquid, that's how we get a superfluid. Superfluid is a particle liquid matter. And string liquid is another new kind of matter. So, and it can be realized in this kind of spin system. And then there's an issue, what kind of interaction can make this string liquid possible? Yeah, it's not easy to design. We can, as a theory, you can just, in one page, you can just write down some formula, and that is a design. And then you give to experiments. Say, experiment title, no, I don't have such a material. This interaction is impossible to realize. So it's just a theory, okay. So actually, it's not that bad, And so string liquid can be realized in some pretty realistic materials. The idea really is the following. So here, it's very common that we may have interaction that two spin want to be anti-parallel. That's what we call the anti-ferromagnetic interaction. The two spin want to be anti-parallel. When two spin want to anti-parallel, they form this. They can fluctuate. This up and down, down up. They form a dimer. They call the spin singlet dimer. Okay. So therefore, because it's an anti-ferromagnetic interaction in the material, spin want to form a dimer. Okay. So here, this bar just means this a spin dimer. It's a pair of spin which are anti-parallel parallel spin. Okay. And why this dimer and the string have a relation is the following. So let's pick any dimer configuration as reference. Then we compare this dimer configuration with any other dimer configuration. That's a blue. Then we put these two dimer configurations on top of each other. Then you can see the red, blue is a string. So therefore, the difference of two dimer configuration is a string configuration. So the dimer fluctuation can be viewed as a string fluctuation. And also, amazingly, this unpaired spin happen to be end of a string. The dangling unpaired spin is end of string. Okay, so therefore we can design some kind of in some material, like in particular this carbon lattice material. It's possible, likely that the spin dimer configuration form a liquid. They fluctuate strongly. They form a liquid, and we call it a spin liquid. And the spin liquid is a string liquid. So, and so that may realize this kind of a string liquid. Okay. So actually, Yun Li used to be my colleague in MIT, and he's a very few experimentalists who believe in theories. We say spin liquid is important. You should really looking for it. And he really tried very hard to look for string liquid. Why I say that? Because how do you look for string liquid? As an experiment, how do you look for string liquid? And so that's a way. You try to make a sample, which is spend months very hard to make a sample. Then try to measure everything you can measure, very hard. And hope you find nothing. When you find nothing, then you discover string liquid. If you find something like phase transition or something, then it's not string liquid. So this is a difficulty because string liquid is a really weird thing. It's not ordinary matter, but our experimental tool and our experimental setup always try to measure something. But the problem is that something is something we know. But the string liquid is something beyond what we know. So whatever you measure is not you want. But he really need to believe this kind of strategy. He need to try to measure everything and find nothing, then get the paper published. So if you don't see anything, but that's a string liquid. But sometimes there's other thing. Once you know there's no conventional ordering, then there's some other experiment you can measure which is supporting, maybe this is an unconventional thing, yeah. And so actually I'm really amazed he really do this, yeah. And so that's also kind of interesting because because we experiment, we do set up to measure something, and something is already known, then it's from theory point of view, whatever you find is not new, So sometimes you need a different thinking, okay. And so actually, you can see this is almost original paper on this system. And this is 10 years, around 10 years, there's a lot of experiments. But this sample is not so good. There's a lot of impurity. So although we have a lot of evidence to say, yeah, maybe this sample have a string liquid, but it's not really smoking gun, not really pinning down. So that's really a very frustrating discovery. It's not like so the problem of this kind of discovery is not newsworthy. It's a discovery span over 10 years, and we still not finished this discovery. So no newspaper or no science news can report this kind of discovery. But once it's really confirmed, it really is a great discovery. Okay. And recently, Lu Li, I think in Minnesota, and he have some new evidence. They see some new phenomena which are associated with this string liquid. And so it looks like we are accumulating evidence and build a stronger and stronger case. And eventually, we may pin down whether this system is a string liquid or not. Yeah. Okay. So actually, this spin have another name called a qubits. You can say spin up is a qubit, is a bit 0, and spin down is a value 1. So a single spin can be viewed as a qubit. So therefore, this our string liquid. Our string can also come from qubit. 0 qubit is a background, and the qubit 1 form a string. Okay. So what that means? That means the string or string net come from qubits, actually. So actually, string and string net is not a thing. The qubit is a thing. So when we say this light and electron and quark originate from the noodle soup, what I really means they originate from qubits. The string liquid is just a name for how qubits are organized. Qubits have many, many different organizations, and one of their organization is called a string liquid or string net liquid. Okay. And this more formal term for this would be the entanglement. The qubits can be entangled, and one pattern entanglement is a string liquid, or the string net liquid, or maybe some kind of membrane liquid. There are all kinds of things describing different entanglement. Okay. And so therefore, this so realizing that, we can say that this interaction, light, electron, quarks, they all come from qubits. That's where they origin. The qubit is a fundamental building block. They all come from qubit. Once the qubits are entangled in proper way, then we can get the Maxwell equation. We can get Fermi statistics. Those properties would come. So that if qubits are entangled in different way, we may not get the Maxwell equation. We may get another wave equation, and we may not get Fermi statistics. Yeah, we may get even fractional statistics. And so therefore, it's really became a slogan that is it from qubits. Everything comes from quantum information. So because everything comes from qubits. Okay. So this really brings us to the movie Matrix. The Matrix is really a movie about this. In the Matrix, I think I don't know how they translate in Hong Kong. And so there's a Matrix describes two words. There's a real material world. That's what we are familiar, the material worlds. Okay. So everything are formed by elementary particle. And there's a virtual world inside the computer. Inside the computer we have just bits. That's the thing about the matrix. It's not advanced enough. They should do qubits. So they don't have classical bits. Okay. But anyway, they say even classical bits is enough. So that's this a virtual world can be as real as a real world. Okay. That's the message of the matrix. It's quite actually I like that movie. But that movie is not quite bold enough. Actually, our real world is even more weird, more bold than Matrix. So what had just happened, if you believe this noodle soup picture, what really happened in our real world is the quantum information world. So the so-called virtual world in Matrix, actually, that is real world. And the photon, quark, electron, they are virtual. They just some organization of the qubits. So the real world is a virtual. It's not real. The virtual world, quantum information world, is real. Okay. So basically that's we really live in the. So everything comes from qubits. In some sense, we can say we live in a quantum computer. The motion of a qubits, the organization, the entanglement, gave rise everything. what I really try to say is that what I try to argue, they can give rise to everything we know, except gravity. But whether what we have is really come from qubits, we don't know. Yeah. But at least if you assume starting from qubits, as theory, we can get everything we have. A standard model, we can get standard model. But without gravity. The gravity is still one problem for us. So basically, it's a summary that the matter space may all come from quantum information, and the light electron quark fundamental force all come from long-range entanglement. So it's very much like the Chinese philosophy. They have a Taiji, that the Taiji is a qubits, okay? The Liang Yi is a two value of qubits, and the Bagua actually the 3 qubits, And so that's but our universe is much more than 3 qubits. To really get this phenomenon, Bagua is not enough. So we need more than 3 qubits. So actually, number of qubits in our universe probably is 10 to the 120, or something of that scale, And so when you have so many qubits, then we have this 积木水火土. That's everything we have. Yeah. And so this is a physics part. Then I want to make a remark on the mathematical side. The density wave in a string actually in Maxwell time gave rise to partial differential equation. That's some kind of new mathematics. Okay. And in modern days, we understand this partial differential equation or Maxwell equation actually comes from fiber bundle, another abstract field in mathematics. Okay. And recently, we realized that this fiber bundle or this string liquid have emergent symmetry, which we call the higher symmetry, which are related to another abstract mathematics called the higher group. And so they're all kind of mathematics of a noodle soup. This quantum mechanical noodle soup encode somehow this mathematics. And also, we also learned that the end of string can be fermionic, or can have fractional statistics. So those is another mathematics called a Brady fusion category or Brady fusion higher category. That's another very abstract mathematics. So somehow this kind of quantum entangled world, this noodle soup describing entanglement, and some very abstract mathematics are somehow related. Okay. And I don't know whether this is accident or not accident. That is a very interesting question. All those mathematical theory are invented due to totally different reason. Why they happen to describe something or a vacuum, for example. And I try to say maybe this is not accident, because the notion of space and the notion of manifold is very fundamental, I think, to both the physicists and the mathematicians. And a lot of mathematical theory we devise probably have some relation to this notion of space. And when you really think about what's the notion of space, the space or manifold is a very weird concept. In some sense, you can say the space is a collection of points. A lot of points is a space. But it's much more than that, because we have a sense of neighborhood. This one point is another point. But how to define neighborhood became very, very difficult. I think one mathematician told me that maybe Gauss really asking this question. This defining manifold in this fundamental way probably is the most difficult. And from this point of view, the sense of space and the entanglement, because this collection of points is like a collection of qubits, but the qubits can have entanglement. And the entanglement gave us a notion of a neighborhood. And so therefore, this highly entangled, many-body entanglement of qubits and the concept of manifold and all this category, hierarchy group, those kind of mathematical theory have a relation. Maybe it's not accident, because mathematical theory, many mathematical theory are designed to describe manifold on some abstract manifold. So maybe it's not accident. And so therefore, the highly entangled quantum system and topological system and this modern mathematics really have very close tie, and so it's a very exciting time. Yeah, thank you.
Thank you, Professor Wan, for the eye-opening talk. I'm quite sure there will be an increase of sales of noodles in our campus cafeteria tonight. So are there questions from the audience?
Okay. I just make a comment for the last slide, 28th slide. You get the 5 elements of Chinese 5 elements. I just add a little bit mathematics right here. So what does the 5 elements mean in the physics or in the string noodles? Anyone? Okay.
I don't want to find me anything, but I think just here doesn't really matter. I don't really mean 5 elements. I really mean those kind of atoms or bubbles or galaxy. It's just everything we see.
But it's not an accident, okay, in mathematics, okay? We have only 5 type of paratonic solids.
Oh, I see.
That's the what is the equivalent?
That I don't know.
Tetrahedron, octahedron, hexahedron, and dodecahedron. That's 5 types, okay? And it can be simply mathematically classified.
Yeah, I don't know whether that's...
That one corresponds to, in the Western philosophy, they use that 5 paratonic solids, okay, correspond to the Chinese 5 elements.
I see. I know, but I don't think there's that connection there. Yeah.
Okay.
It's really this elementary particle coming from those entangled qubits, and from elementary particle we get all these other things. That is a picture. So actually, this picture, in some sense, this picture I put there, this picture actually represents the reductionist point of view. That is, there's an elementary building block. We just assume it's there with certain property. Then everything else coming from this fundamental building block. So what we have here described is a little bit emergence point of view. That we don't emphasize it on the elementary building block because they're too simple, just qubits. We emphasize more on how qubits are organized. So we view organization as origin of other things. Because the building block is too simple, so we don't think of them. But there's actually, the qubits have many different organizations. Different organizations which give us different universe. That universe will have different physics law. For example, there's one universe that may be superfluid. We don't have longitudinal wave. And our universe is actually highly non-trivial. Because our universe have a wave with a 2 transverse mode. That already means that the vacuum in our universe is highly entangled. It's a highly non-trivial universe. But you can imagine there's some other universe, the qubits have a much simpler entanglement. That universe will be very boring. Probably that's why we don't see them, because that universe cannot support human beings. Only when the universe is complex enough can support a human being and try to figure out what the universe is.
Okay. The real question, okay, this is not, 5 elements is not a question, okay, that's really. The question is, when you showed some slides, I found that there is a pattern, okay, with the circles and the strings, okay, and this is 2-dimensional, okay. The 2-dimensional figure. You showed several slides, okay, over there, like waves, okay. You see that one?
This is.
The question is that our universe is the way we perceive it, okay, it's 3-dimensional, okay. And this 2-dimensional is one, we can think about it as one section. Now, if you put more sections, if you just move this down, okay, what's the solid picture? Solid picture, if we like a circle and one, okay, that one is a continuous move. Okay, suppose we have that one, we get some surface.
This picture is 3-dimensional. It's very hard for me to draw a three-dimensional.
That's a 3-dimensional case. That means this kind of continuous. That would be the.
But what I really mean is 3-dimensional string.
That would be 2-dimensional surface. Is it?
No, I really mean 3-dimensional string, not 3-dimensional, not membrane liquid in 3D.
In 3D, what is this one?
Liquid in 3D, not the membrane liquid. The membrane liquid is different. But here I do mean string liquid in 3 dimensions.
In 3 dimensions, it's also
Also
string
string
liquid.
liquid.
It's just string next
Yeah, that,
okay,
this is not the
one
slide.
dimension, one-dimensional
One-dimensional
elements.
string,
Okay.
yeah.
Oh, okay.
3-dimensional space, but a one-dimensional string liquid.
Uh-huh.
I still mean that.
Okay,
Yeah.
you still say, okay, one dimension,
I see.
not 3-dimensional in the three,
Yeah,
not
not
two
the
dimension in
slice,
3 dimension.
not the membrane liquid. Yeah.
All right,
And,
thank you. Okay.
So actually, it took me a long time. I think I wrote the code to produce this animation. It took me a few months to do that. And that's also related to HKUST. I think once I was asked to give some public lecture, the audience is supposed to be high school student. And so it took me a long time to do this. And but indeed, this string liquid, but however, membrane liquid is possible. You can, why not extend a membrane liquid? And once we saw that maybe you can use a membrane liquid to describe a gravity. The gravitational wave, or maybe the wave in the membrane liquid.
There's some kind of Young manifold inside the liquid.
No, this membrane is random. It's not Calabian, just a random membrane. But unfortunately, the membrane liquid don't work, you know. Yeah, and they produce something different, but not Einstein gravity. Yeah, and but we don't know. So actually, that's why we stuck. We don't know what kind of weird noodle or membrane which gave rise to Einstein gravity. Yeah.
Thank you, Professor Wen, for the very inspiring talk. So may I ask, in your theory, you must have Lorentz invariant, right? So
Yeah.
is it an emergent symmetry in your theory?
This is another difficulty of this theory. But this is not too big a difficulty. It's really following. This theory is not a naturally Lorentz invariance. Because usually, certainly when you do this kind of wave, we don't have one wave. Then this wave won't have one velocity. But however, you can see in the string net liquid, you may have a wave of electromagnetic wave and also Yang-Mills wave. And in this kind of system, it's not natural for these two waves to have same velocity. So it's very natural they have different velocity. And also, so therefore, we don't naturally have a Lorentz invariance. But however, we naturally have a linear dispersion relation, but just with different velocity. To have same velocity, one need to fine tune. So therefore, to obtain Lorentz invariance, we can get that, but not naturally, which require fine tune. Actually, this reflects another very fundamental difficulty. The Lorentz invariance is some equivalence between space and time. But the theory I'm doing here is quantum mechanics. In quantum mechanics, space and time are totally different. So there's no natural relation between them. So right now, I don't know what to do. And so if you really think of Lorentz invariance as something very fundamental, maybe it is fundamental, then one has to abandon quantum mechanics. So one has to really invent a different quantum theory where space-time are more or less at equal footing. And so actually, this is a very good thought, you know. At the moment, we think our theory is very, very complete, seems to answer everything. But let's just like beginning for 1900, you know, everything is known, but only just a few dark clouds. But then that led to so much quantum mechanics.
Right.
I don't know whether Lorentz invariance and their hint, the space and the time should be equal, is one of the dark clouds. We should really handle that. But handling that really probably means to really go beyond the quantum mechanics.
Right.
You know, I'm condensed matter physics, I cannot go beyond quantum mechanics, otherwise I cannot get my funding. But the people in high energy field theory can be more bold, you know, can go beyond that.
So you mentioned you mentioned entanglement many times.
Yeah.
So your string net, your strings, when you go to quantum mechanics, you introduce the superposition of this different string configurations.
Yes.
Is it because of the superposition principle?
Yeah.
Is it how the entanglement came in?
Exactly.
Okay.
Yeah.
So,
and also, yeah, indeed, the entanglement really have very close tie with the superposition principle.
Right.
And that's one of the most amazing thing about quantum mechanics. Because actually, when writing this talk, I was thinking how much I should do quantum mechanics. Then I feel I really want to do that, maybe I need another hour try to explain the superposition principle. But on the other hand, the superposition principle alone is not enough. There's another important feature, kind of tensor product decomposition. It's, and that's also very important. So these two together gave us this entanglement. Right. So that really says that this very two principle, this superposition principle and the tensor product decomposition, right. These two things play key roles. Right. So this became our starting point. Then you can ask deeper question, where this come from?
Right.
Yeah.
This is,
in particular, why we decompose a certain big Hilbert space in certain tensor product. You can choose under different tensor product basis. How that play a role? I don't know, but again, right now, I really don't know anything, but I still want to bravely say, maybe the general equivalence principle coming from there. That is, given the same Hilbert space, they can have different tensor product decomposition, and there's some symmetry relation between that. And so I feel that may have something to do with the general equivalence principle in general relativity. Yeah.
Thank you.
Yeah.
The entangled cubic is a very interesting idea. I just wonder, based on your idea or model, can you predict that in nature there's only 4 fundamental interaction or fundamental force?
No, one cannot.
And also, can it explain the gravitation and the building into this entangled cubic idea?
Thank you for the question. First, we don't have a theory for gravity, so that's out. And then we cannot explain there's only 3 interactions. Because dependent on entanglement, different entanglement can give rise to different number of interaction. Okay. But however, the question is, that's the real question is that whether there is some kind of falsifiable prediction from this picture. And the answer is yes. And the key point here is that everything comes from qubits. So fermion is not fundamental. And this point of view have a prediction. That is, there's no neutral fermion. Every fermion must be a gauge charge. So that is a prediction. So actually, in the standard model, we find we do have a neutral fermion. There's some composite fermion, which is a totally gauge charge neutral. And that is a contradict with this qubit picture. Okay. So the prediction from that, this so-called neutral fermion in a standard model actually is not neutral. There's an additional gauge field, maybe Z2 discrete gauge field. And this fermion may carry that kind of gauge charge. And that gauge field would carry, will have a gauge flux. So the prediction is that there must be, if everything comes from qubits, then there must be new cosmic string beyond the standard model cosmic string. So there's a new gauge field, new cosmic string. And but this is a very, very rough, it's still falsifiable, but it's very hard to test experiments. But at least say there's something. And so indeed, there's a lot of mystery in standard model, and it's very, very worthwhile to using this emergent picture, because emergent picture have more constraints. Let me give another example. Like SU5 ground unification have a neutral fermion, no gauge charge. But SO10 ground unification have no neutral fermion. So therefore, this theory prefer SO10 ground unification. And so SO10, actually, I have a paper that says SO10 ground unified theory can emerge from this qubits liquid because it have no neutral fermion. And so it gives some preference. And we also know that SO5, SO10, and Luanda, some global property are different. So I'm hoping this qubits model is like one kind of a beyond standard model. Maybe there's certain global property maybe different, or maybe there's something like there's also paper about the strong CP problem and also some other thing, whether one can have some new new look. And yeah, actually, I really feel this is a very exciting direction. And actually, I myself thinking to go into that direction, but a lot of learning, because to learn particle physics or the phenomenology is not easy. And you have to understand the problem or some non-naturalness also not easy. But I feel that I really feel that if there's some collaboration, and then try to looking for those standard particle physics from some different angle, whether there's some new insights. Yeah. So right now, what I just said is some very, very broad things. One should go to some more detailed, measurable things to see whether there's some insight there. That I don't know. Yeah. So we don't have that yet.
So what would happen if you try to do the Michelson-Morley experiment in a bowl of noodles?
Yeah. And so actually that experiment basically say there's no ether. Okay. And I think that's the wrong interpretation. And so the issue is about this low energy effective theory. Whether low energy effective theory have a Lorentz invariance or not. I think in that experiments, what you measured, including the measurement equipment, all low energy, they're all part of low energy effective theory. And then in this setting, there's no way to detect this anything non-Lorentz invariance. But however, suppose the Lorentz invariance is emergent, means at high energy, actually you have violation of Lorentz invariance. Then if you use this very high energy, like a dark matter particle, to make your equipment, maybe you can see difference. So you need to using material made by particle which are already high energy particle violating Lorentz invariance to measure the breakdown of Lorentz invariance. Yeah, so that's my question. So because atom, quark, proton, they all belong to low energy effective theory. They all have Lorentz invariance, so you cannot detect thing. Yeah.
So has anyone looked for that in these kind of condensed matter analog systems?
Yeah, in condensed matter it's very common. The Lorentz invariance is always emergent. So actually, it's okay to have something go beyond the speed of light. You get this chunk of radiation, and then you can using you need to break Lorentz invariance to measure to measure some effect. That's the thing. But in condensed matter, it's easy to do that. Yeah. Yeah.
3 questions. I really like your view of the universe. And can you first answer my question is, what do you think, do you really think the universe, we are part of the universe, or we're just living inside the universe as a quantum computer?
I don't know what you mean.
You said we are living inside the quantum computer, right? Or we're part of the quantum computer, because we all are the excitations of your string network.
I don't know.
Right?
I think we believe we are made of atoms. The atom made of quarks, and the quark coming from the string end. So I don't know how you translate this into your language. Whether part of the universe, not part. We are end of string. Let me put it this way.
All right. And second question is we know for particles there's elementary charge, and your charge, according to your theory, all strings starts from charged particle, right?
No, it's the end of string is a definition of a charge.
Okay, it's fine.
The string itself is just qubits.
It's not a question about charges. It's about the what is the mechanism that you think that is holding up all these strings to a certain location that creates the charge?
Yeah, this is I don't know how to say that. You can see, we assume, actually what we have here, assumption is that the vacuum like a qubits ocean, just a lot of qubits. But then you may ask, what determines the location of qubits? But when you ask this question, you assume there's something between qubits. But here I want to say that the space and the sense of space coming from qubits, there's nothing more fundamental than qubits. So there's no between qubits. That notion do not exist. So in a sense, the notion of something between, we have two things, there must be something between the two things. It's a classical notion that we firmly believe the continuum manifold. And this continuum manifold actually is mathematics very hard to define. Actually, real numbers do not exist. If you think about how we define real number, you'll see real number is an emergent phenomenon. They do not exist. The same thing here, that there's nothing between qubits. But however, far away from, at a longer scale, the sense of continuity comes from entanglement between those neighboring qubits. So actually, the sense of a manifold and continuum, sense of continuum coming from those entanglement. So therefore, the sense of location, metric, they're all coming from these discrete things. So this really is the heart of quantum gravity. We start with qubits and their entanglement. Then we want to obtain a manifold with a metric, with a curvature, all this notion. But they are very far from qubits and the linear algebra, and how these two can connect. That is a very fundamental question. So similarly, the location of string is maybe, I don't know whether it may be similar. Just some qubits is up is a non-string, some qubits down is a means string. Yeah.
All right. Final question. So if you go to a sailing class, the first day you learn about how to make joints and knots, right? Do you think at the ends of the strings you have here, could there be any new physics about how you rotate and make knots at the ends of all these strings?
So actually the knots actually became important, but only in the sense when we describe this fractional statistics. No, where is this? Yeah. So like there's like exchange and reconnection. So here, this kind of a picture relate to somewhat knots. When things get knots, the string with knot and string without knots may differ by some amplitude. This amplitude is associated with statistics. Actually, statistics is not only just a boson-fermion. In 2 dimensions, it can be more complicated. And also, there can be statistics, mutual statistics between particle and the strings. They can braid around each other. So actually, statistics is a very, very complicated topic. That's what we require the so-called fusion category to describe it. But that's also related to knots. In a sense, this kind of thing related to this so-called braid group representation. And the braid group and the knots are also related. So those kind of knot theory and so it's related. So actually, that's a part of this this braid fusion hierarchy category I just mentioned here. So this is related to knots. Yeah.
In the interest of time, maybe we should close the formal session here. But please join me in thanking Professor Wen again. Yeah.
Thank you.